and materials. In the previous two lectures we discussed different types of material in general which are applicable for marine environment. We discussed about properties that are exclusively required for material to qualify them to be used in marine environment. In detail we discussed about steel as one of the important construction material for ocean structures in the last lecture. In this lecture we will discuss about some additional material which can also be used as construction material for offshore structures. So this lecture will focus on concrete in marine environment. In addition we will also talk about fiberglass, tempered glass, concrete, wood, buoyancy material, coatings and summary of the selection of material in this lecture. In the next lecture we will dedicate completely to the response behavior of concrete alone in marine environment. In this lecture we will of course however touch concrete as one of the important material for construction along with other material as listed here in this slide. Talk about fiberglass as one of the important construction material used for marine environment. Most prominent non-metallic material is a fiberglass which can be used for ocean application. What we use in ocean application is actually a reinforced fiberglass which is reinforced with plastic. We call this as FGRP or simply FRP. Small boats and buoys are generally made of FRP. There are many types of composite material in fiberglass which are modified constituents which qualify this material for marine environment. Composite materials consist of reinforcing material of fibrous nature and a bonding material which forms an homogeneous mass which can be used as a construction material for marine environment. The reinforcing material to this kind of composite actually gives strength to the structure. Consists of glass fibers, carbon graphite, nylon, silica or sometimes metal wires such as steel, aluminum, boron and tungsten which are actually used as reinforcing material or fibrous in nature which is coupled with the bonding material to form a composite of fiberglass which can be used as one of the important construction material in marine environment. Bonding material are typically epoxies, polyesters, phenolics and silicon. Most common is a glass fiber with an epoxy or a polyester binder. Strength of this kind of composite fiberglass depends on the manufacturing process also. The performance characteristics vary from different manufacturers as well. Fiberglass polyester mat is widely used in the production of small boats and buoys as one of the classical material for construction of these kind of small vessels meant for navigation. The major advantage of fiberglass composite as a construction material in marine environment is free of maintenance and its durability under variety of operating conditions. Fiberglass has specific problems which need to be addressed before we recommend this material as one of the construction material in marine environment. Fiberglass actually has a specific problem. Owing to its internal damping characteristics, fiberglass generally get heated up when it is subjected to fast changing stress cycles. That is one of the important demerit or one of the specific problem what fiberglass has, because in offshore structural construction system you will see there are members which will be subjected to fast changing stress cycles. In those criteria situation fiberglass cannot be recommended as one of the important construction material for these systems. Fiberglass reaches its fatigue strength at 10 million cycles. What does it mean for us is that the ratio of fatigue strength to tensile strength is as low as about 0.25. It means the fatigue strength of fiberglass, even composite, is also much lower to that of the tensile strength of these fibers. If you look at the behavior of fiberglass composites under marine environment, fiberglass loses its strength by absorption of water. when immersed over a long period of time or even when it is exposed to ultraviolet rays. Remedial measures to treat this problem is that to apply appropriate coatings on this. Absorption of water actually results in substantial decrease in compressive strength also. Ultraviolet rays causes brittleness to the material. Fiberglass tends to laminate upon the application of heat. Very important caution is that more fiberglass resins will burn at high temperatures. If you look at the manufacturing process, high quality and standards are necessary to obtain the desired strength, and of course the resins which are used in manufacturing fiberglass composites are effectively designed to modify the fundamental characteristics of fiberglass which suits for marine application, which can overcome few of these problems which are listed above in this slide. The next material can be, instead of a fiber reinforced glass or a composite, we can look for what we call tempered glass. Glass shows a substantial promise as a material when used in compression. However, since offshore structures are encountered by combination of variety of loads, we cannot ensure that the member of structural components in offshore structure are subject to only one classification of loads. Generally they are always in a different combination of loads, and therefore the mechanical characteristics of glass need to be substantially modified if you are going to use glass or a tempered glass as one of the construction material in marine environment. Further difficulty arises because of non availability of glass in large sections without defect, because glass in the manufacturing process has attracted lot of defects during the construction process. So it is very difficult to have a large section of glass without defect. So these two limitations pose tempered glass as one of the serious problem which cannot be used as directly as a construction material in marine environment. The other material which is very popular in case of, let us say, gravity based structures, in case of top deck sites, in many of the offshore platform systems, is concrete. Concrete has got many advantages and therefore strongly recommended as a construction material in the marine environment. It has got excellent compressive strength, resistant to attack by seawater. Problem of low tensile strength, which is one of the phenomenal difficulty what concrete has, is generally overcome by providing necessary reinforcements to this concrete. Pre-stressing or ferro cement are also desirable methods of strengthening concrete. Ferro cement actually consists of wire mesh reinforcement that gives considerable stability and permits some tensile stress in concrete. Ferro cement is widely used for construction of barges and boats. Pressure vessels for LNG storage are generally constructed using pre-stressed concrete. Concrete suffers serious deterioration during freezing and thawing, and therefore one has got to be careful in treating this material if it is to be used at different temperature gradients in marine environment. Wood is also one of the interesting and important construction material which is used in marine environment. Ladies and gentlemen can easily recollect that until recent times wood has been one of the non-replacement material for construction of ships. It is one of the oldest material used in marine environment. For many years basically it is only material which is used for shipbuilding, extensively used now for piling, docks and other similar applications in marine environment. In the recent past, wooden laminates also being used as structural members in offshore structures. Let us look at some buoyancy material which are also used in offshore construction applications. Materials which have low specific gravity lower than that of water are generally identified as buoyancy materials. When integrally included in underwater structure, they provide enough and required buoyancy to the whole structural system. Few common application areas where buoyancy material can be commonly used are small submarines, oil well drill pipes and deep sea buoys. Most common material which is used as a buoyancy material is wood. the specific gravity of wood is approximately equal to 0.5, whereas one can use gasoline also whose specific gravity is about 0.7. However, there are some desirable characteristics which a buoyancy material should possess. For example, it should have no water absorption and it should have no disk configuration under compressive forces. Syntactic foams are also recently being deployed as buoyancy material to cater to the above requirements. These are hollow glass spheres dispersed in a plastic matrix. They have a very high compressive as well as shear strength. Most efficient syntactic foams use glass spheres or of extremely small diameter. They are identified in literature as micro balloons, and of course an epoxy resin binder is being used to form a good binding material of these glass spheres of a very small diameter. We call this material as syntactic foams. They have a very low water absorption capacity and they can be easily handled with woodworking tools. So, the workability or constructability with respect to this buoyancy material as syntactic foams is as similar to and as easy as that of wood. Therefore, this is one of the popular material which is being used as construction material in offshore structural systems. Next comes in the list is different kinds of coatings. Ladies and gentlemen, we must understand the importance of coatings in marine environment. Coatings are extensively used in marine environment to protect surface against deterioration from salt spray, barnacles, corrosion prevention, pollution and all other contaminants which are present in seawater. The fouling increases with the increase in water temperature. Now, plastic coatings which are new recently in the literature are being used in the recent past for anti-fouling protection. Certain epoxy coatings are also used for corrosion protection as well in some of the members in offshore structural systems. Coatings actually serve as a physical and a chemical barrier and prevent material degradation the moment they are applied in a proper format. Now, what is that proper format which we must apply coatings on the members? Protective coatings are generally applied up to 5 coats, resulting in a film of about 0.25 to 0.5 millimeter thick in total. Polyurethane coatings have been successfully used for protection of wood also in case of marine applications. Most common anti-corrosive coatings which you can see in the literature are listed as follows. You can say coal tar epoxy is one of the common anti-corrosive coating which is being used. You can also use epoxy, polyurethane, vinyl anti-corrosive coatings or neoprene coatings and other rubber coatings which are found in the literature as recommended strongly as one of the possible anti-corrosive agents which can be applied on members of offshore structural members to prevent it basically from action of corrosion. Ladies and gentlemen, we will discuss the corrosion process phenomenally in detail in few lectures down the line in this same module. We also talk about another material which is an important application in offshore sector, which is GRP. GRP is essentially used as one of the interesting and recommended material for construction of lifeboats. They are self-righting, totally enclosed, motor propelled survival crafts which are used in offshore oil industry, which are manufactured using glass reinforced plastic, which I call them as GRP. One important property what the GRP attains is fire retardant resins. The craft range of 6.2 to 8.75 meter in length, which can carry about 21 to about 66 people, are generally used or generally constructed using GRP as a material. The survival craft, which is required to withstand about 30 meter high kerosene flames and temperature about 1150 degrees Celsius, are all essentially fabricated using GRP as one of the important construction material. There are some few lifeboats, boats and ships given as examples in this table. For example, Inshore IB1, Atlantic 21, Atlantic 75, Mersey, Trent, Arun, Severn are some of the important names of the lifeboats and ships which has been used as survival crafts in offshore industry. They are introduced in different years as you see here as old as 1971 to as new as 2003. They have a displacement value or weight as stating as low as 338 kilogram to as high as even 27 or 31 or even up to a displacement of 41 tons. The size of these life crafts or lifeboats vary anywhere from 4.952 meter to as large as 17 to about 16 meter 6 meter as well. They can travel in various speeds varying from 16 knots to as high as double of this, which is 32 knot speed. The essential material which has been used for construction, or you can see here essentially GRP or fiber reinforced composites. You also use FRC, which is called fiber reinforced composites, which has been used essentially as one of the important construction material for construction of survival crafts or lifeboats and ships. Here is a photograph you see is a ship built with monolithic GRP with displacement 450 tons and about 46.3 meter long. This is another photograph with a Sandvik construction of GRP and fiber reinforced plastic. The displacement is about 600 tons and the length of the ship or the boat is about 73 meter long and the quoted speed of this is about 35 knots. Ladies and gentlemen, we are strategically hiding the name of these vessels because of important naval importance which has been done in the literature. Now the fundamental question comes to our mind is, why do we study behavior of materials in marine environment? What is the necessity to understand behavior of material in marine environment? Most importantly, legislation calls for a periodic certification of offshore structures. It is very important that every offshore structure should be periodically certified for its survivability in the given sea state or in the given sea environment. Alternatively, one can rely on the structures to do so well designed and are built so that no serious failure can develop during their working life. However, unfortunately the weather conditions and marine growth become more severe than initially predicted values in the design, and therefore waves and current loads are also being underestimated in the few design cases. Fatigue and corrosion are still a debatable subjects which are very essential problems as far as structures in marine environment is concerned. All the above factors result in a heavy penalty on the existing weight of the structural system. Otherwise, if you are able to predict all of them in a proper format, one can save large sum of material cost and there can be even easiness in the installation procedures as well. But since we are unable to predict all the above factors in a very high precision manner, we have got to account for this correction factors in the material only. Therefore, it is very essential that we must study the behavior of materials in marine environment. So, feedback of actual conditions of structures during their working life will be a very helpful tool to do the design successfully for structures to be designed in marine environment. Now the question follows is, what are those specific problems which are faced by different materials or structural members when they are put in ocean environment? This is a very interesting question which we would like to answer before they understand the variety of material which has been used or recommended for ocean environment. Let us look at steel as one of the important material which has been very commonly applied and used in ocean environment. Steel develops cracks and it is susceptible to localized corrosion effects. Cracks occur in heat affected zones in the welded tubular joints which are located in splash zones. The local corrosion is enhanced due to the presence of steel wires or chains in the tubular members. If you look at concrete as an alternate construction material for steel in marine environment, then concrete is a problem because the deterioration phenomena of concrete in offshore environment is very little known in the literature. If you look at pipeline risers as one of the important material which is being used or the member which is being applied in offshore structural system, due to thermal variations, high internal pressure in the pipelines, environmental loads acting on the pipeline and relative motion between the platform and the pipeline, in case of gravity structures they are subjected to a combination of different variety of loads which are specifically not to be understood, because the problem is still the research updates us the behavior of these structural members under the combination of these kinds of loads. Therefore, it becomes very critical for us to understand the material behavior under this combination of loads for any structural member, for example pipeline risers. If you look at concrete for marine environment, strength and durability are very important parameters of concrete in marine environment. The concrete mix should be carefully selected on the basis of its shear strength, bond strength and workability, because underwater placement is one of the important criteria which we considered in mind when we select concrete for marine environment applications. Corrosion is another phenomenal problem what the material has. Essentially all metal components suffer corrosion due to some extent because of action of water and environmental effects on this material. Metals often corrode due to electrochemical action, but we call them as wet corrosion. Non-metals are attacked by chemical corrosive media, which we call them as dry corrosion. So corrosion is an inherent process which is present in the ocean environment. Therefore effect of corrosion on metal as well as non-metallic components are always present, and the effect causes a very serious problem to these materials and of course to the members made up of these materials. The primary zones of corrosion in any type of offshore structures can be the following: immersed zone, splash zone and atmospheric zone. Atmospheric zone is the uppermost zone layer which has got the corrosion rate of about 5 to 10 mpy, that is mils per year. The control methods which are generally employed to protect or to prevent or to retard corrosion in the atmospheric zone is you can apply coatings, can use epoxy based resins, can use chlorinated rubber, vinyl, zinc sulphide, etc. If you look at the splash zone, the corrosion rate is very high, it is practically about 5 to 10 times as that of atmospheric zone. So 55 mils per year. Generally the control methods are coatings and provide additional cladding. If you look at the immersed zone, the corrosion rate is half that you have in the splash zone, it is about 25 mpy. The control methods are generally cathodic protection or some coatings. Now in the whole literature you will see MPY stands for mils per year, and 1 mil is about 1/1000th of an inch. So if you compute for example 10 mils per year, you will see what would be the thickness in terms of millimeter of the corrosion. So corrosion actually eats away the parent material in terms of its thickness. As we all understand, once the designated thickness of a material in a tubular joint is lost, the member also substantially loses its strength, or the member degrades from its functional purpose for which it is being designed. So corrosion as a deteriorative process should be addressed very carefully. We have a dedicated lecture explaining corrosion and protection measures on corrosion subsequently down the line in the same module. If you look at the material selection which is being advised by different codes based on BS 7191, EN 10225 or APA grades, I have put a brief summary of different kinds of recommendations made by these international codes on material selection for different typical grades. Module walls and decks, if you look at this as one of the important application area, the minimum nominal yield strength recommended by these codes vary from 275 megapascal to 355 megapascal. The typical grade recommended by these kinds of codes goes as 275D to 355D, and these numbers exactly reflect the same strength which has been suggested by these codes. So 275D stands for a grade of steel which has got a minimum nominal yield strength of about 275 Newton per mm square. If you look at different kinds of members varying from modular supports, cranes and topside deck members, then they require a higher grade of yield strength. Therefore people recommend yield strength with 420 to 460 megapascal. Therefore we have got these kind of grades recommended by different international codes, and of course most important requirement suggested by these codes is that through thickness ductility is demanded from this material when they are being used for this kind of specific application. If you look at floating facilities like buoy, semi submersibles, etc., then the nominal yield strength required for the material to be used for floating facility can vary as low as 235 to 355 megapascal. The different grades of steel recommended by these codes are listed here. If you look at the jacket legs and module support frames in a jack-up legs, or in case of jacket platforms, then you require yield strength steel varying from 355 to as high as 460. If you look at the nodal joints and other areas subjected to through thickness stresses, then you require again yield strength as high as 460. Of course, additional requirement suggested by the code is through thickness ductility is ensured or should be checked so that they can survive the specific condition for which these stresses are subjected to. If you look at the steel piles as one of the important members of offshore structural system, then they require yield strength varying from 355 to 460. So ladies and gentlemen, this table gives you a comprehensive lookout of how international codes recommend material for different kinds of application as a summary here. If you look at material selection as one of the important criteria in offshore structures, structural steel which are used in offshore structure should follow essentially recommendations made by API or AISC or DNV guidelines. Many offshore structures are made of hollow steel tubes. The minimum requirements of fabrication service should follow API codes as ASTM, A139, A252, A381 and A671 as mandatory requirements to qualify them to be used in offshore structures. Steel are also grouped according to the notch toughness characteristics as imported in impact tests. We have already discussed in the last lecture. I want to slightly elaborate more on the notch toughness specified by different tests. As we see, steel can be grouped as class C, class B and class A. A is applicable at sub-freezing temperature, B is applicable for material where the thickness, cold work stress concentration, impact loading can be overseen in the design, whereas class C is applied only when no impact tests are specified. It is used for primary structural members involving limited thickness, moderate forming, low restraint, modest stress concentration and quasi static loading. The example can be a piling or a jacket braces and legs, deck beams and legs, etc. So you will see in case of selection of steel or grouping of steel by international codes, notch toughness or impact test serves a very important purpose. I will come to that in the next slide. So selection of material other than steel is insisted based on Charpy V-notch test, which we call CVN impact test. CVN impact test is a very simple experiment conducted in the laboratory to understand the impact strength of any material. So it is a standardized high strain rate test which is seen in the standard test procedures. It determines the amount of energy absorbed by the material during fracture. Absorbed energy is given as an index of notch toughness of the material. It is a tool to study the temperature dependent ductile brittle transition. The test unfortunately gives only comparative results. If you look at the different failure modes that affect material under loads, different types of failure modes are encountered by the material when they are exposed to offshore structures. For example, buckling, corrosion, creep, fatigue, hydrogen embrittlement, impact, mechanical overload, stress concentration cracking, thermal shocks, wear and yielding are very interestingly a wide variety of failure modes which happens on material when they have been used in structural members in offshore structural systems. We look at the test procedure of impact test suggested by Russell and Charpy in 1901. It consists of a simple pendulum of a known mass and length. It is dropped to cause an impact on the notch specimen of the material. Energy absorbed is inferred by comparing difference in height of the hammer before and after fracture. Notch in the simple affects the test results. Results are influenced by the notch dimensions geometry. The specimen dimension recommended for this test are 10 by 10 by 55 millimeters. These tests provide me quantitative and qualitative comparative results. If you look at the quantitative values given by this Charpy test results, the energy required to fracture the material can be used to measure the toughness of the material. It speaks about the yield strength of the material. The strain rate can also be studied at which the material fails. Importantly, the test gives me ductile brittle transition temperature. This temperature derived where the energy is required to fracture the material drastically changes when the test is being conducted. The test also gives me some qualitative results. It can be used to derive ductility of the material indirectly. The material breaks on a flat plane, then the material is considered to be brittle. If the material breaks on a jagged edge or shear lips, then the material is considered to be a ductile material. Usually fracture will be a combination of flat and jagged edges. So this determines what is the percentage of brittleness and ductile failure or fracture in that specific result. This table gives me a comprehensive comparison of material selection requirements based on ABS requirements as given here. This gives me different grade of steel being used for secondary, primary and special applications in different service temperatures, both given in Celsius as well as in Fahrenheit. So interestingly, ABS designates steel grades based on their applications, as you also saw in API and British standards and DNV rules. Generally, weldability is a very important characteristic which is a requirement for an offshore structural member. So weldability can be computed by computing the cold cracking susceptibility and carbon equivalency as given in the following two equations. If you know the carbon, manganese, nickel, copper, chromium, molybdenum and vanadium composition in a given material in percentage, you can easily find out what we call carbon equivalency and cold cracking susceptibility. For a given material, maybe steel which is having chemical composition of a different nature, these percentage of composition are available in the standard literature. So for any specific grade of steel, you can always find out the weldability based on the PCM value and C equivalent value as seen in this slide. So ladies and gentlemen, mechanical properties of steel should be based on tensile test as well as Charpy's V-notch test. These are the two recommendations made by international codes for people to understand how do we select material for offshore application. Charpy's V-notch test results should be obtained with longitudinal axis parallel to the direction of rolling. Steel should be heat treated as far as they have been used or recommended to be used in offshore application. If you want to use steel as a material for offshore drilling unit, then steel should be used as a material. In such cases, formability, weldability and toughness are important criteria to be checked for recommending steel for offshore application in case of drilling units. If you want to recommend material other than steel for drilling units, then you must focus on mechanical properties, toughness, fatigue and corrosion characteristics. In case materials are used in combination of steel, then you must also check for the galvanic effects which should be considered before you select that material for offshore drilling units. Now ladies and gentlemen, we will give a very brief summary of different kinds of material which have been recommended for offshore application. We have seen them in the past 3 lectures. Now down the slides, few slides will give you a very brief summary of all the material which has been discussed in these 3 lectures for your apprehensive knowledge on material selection in offshore applications. Steel, you can use low carbon, low strength steel. It is essentially used for drilling and production platforms, submarine pipelines, hull structures, buoys and instrument fitting as well. If you look at medium strength steel, you can use it for buoys and icebreakers, use it for submarines, you can use it for pressure vessels, storage tanks and merchant ships, etc. If you look at high strength steel, then you can use it for pressure vessels of desubmergent search vehicles. You can use it recommended strongly for jack-up rig applications because you require steel whose strength is as high as 600 megapascal plus for jack-up rigs. If you look at copper and its alloys as construction material for offshore structures or marine application, protection of offshore structure splash zone is generally done by monal sheathing, which is in copper alloy. It can be used for heat exchangers, can be used in condensers, used in pumps and valves in topsides, can be used in pipe works aboard ocean going vessels, can be used in desalination plants as well. If you look at, ladies and gentlemen, aluminum and its alloys as one of the construction material for marine application, It can be used for sacrificial anodes, it can be used for wave energy, that is OTEC wave energy converting devices, can be used in deep submersion vehicles, can be used in hydrofoils, deck houses, life saving equipments, ventilation ducts and stack enclosures as one of the important applications. If you look at titanium and its alloys as material for marine environment, then you can use pressure hulls for deep submersibles, structural members for high speed ships, heat exchangers in vortex system. If you look at lead as one of the material, it is a most suitable material for ballasting. If you look at plastics, can be used for insulators, shock resistors, equipment cabinets, pressure hulls which is glass reinforced plastics which we call as GRP, piping gaskets, etc. If you look at elastomeric material, polymers having elastic properties of natural rubber is what we call elastomeric material, then they can be used as insulators, diaphragms, shock absorbers, coatings, buoyancy bladders and hoses, etc. If you look at wood as a construction material in marine application, most commonly used for ship structures, pilings, docks, wharfs, equipment containers as well. If you look at concrete as one of the most preferred material in marine application, plain concrete can be used for coastal and ocean structures or offshore structures, polymer concrete can be used salvage of damaged concrete structures in splash zone and zone control corrosion concretes. Fiber reinforced concrete can be used for construction of barges and external coating of submarine pipelines, whereas lightweight concrete can be used for construction of living quarters on the top sides of the platform. Thank you very much. We will see the next lecture concrete as one of the important construction material, what are the problems faced by concrete in marine environment. Thank you very much.